name is Sandra Brooke. I'm a member of the research faculty at Florida State University in the US. I will be giving this lecture on the biology, ecology, and conservation of deep water corals. These may also be called deep sea corals or cold water corals. The term coral can include a number of different taxa within the phylum Cnidaria. There are many definitions for coral, but the most comprehensive I found was coined by Dr. Stephen Cairns in his 2007 paper. He stated, corals include animals in the Cnidarian classes Anthozoa and Hydrozoa that produce either calcium carbonate secretions resulting in a continuous skeleton or as numerous, usually microscopic, individual sclerites, or that have black horn-like proteinaceous axes. Of the 7 taxa that fit this definition, only 5 occur at depths greater than 50 meters. This depth follows the U.S. National Oceanographic and Atmospheric Administration that classifies all corals living at depths greater than 50 meters as deep-sea corals, although most live much deeper than this. This table shows the important deep-water coral taxa highlighted in yellow, together with the total number of species and those that live greater than 50 meters depth. It is clear from these numbers that the octocorals in the subclass Alcyonaria are by far the most diverse group in both shallow and deep water. The next most species group is the Scleractinia, but only a few of these form deep reef structures. Unlike shallow corals, which live mainly in the tropics, deep corals are globally distributed, usually at depths greater than 200 meters. The depth distribution seems to be driven by temperature rather than depth per se, and in places where cold water occurs in shallow depths, the corals are sometimes also found there. These types of areas include fjords where offshore water is funneled into narrow spaces, or cold regions such as Alaska. Most corals occur on topographic features such as seamounts, rugged slopes, or canyons where currents are elevated and hard substrate is exposed. Some corals are found in soft sediment, but most require hard substrate. As their name suggests, stony corals all have hard skeletons composed of a form of calcium carbonate called aragonite. Those species that occur below 50 meters are all azoxanthelate. Most are solitary and most require hard substrate for colonization. Of the 14 species of deep water branching stony corals, 6 can form complex structures. Unlike shallow reefs, which are constructed by boulder or plate corals, all deep water reef building species are branching. As the colonies grow larger, the inner branches die and fill with sediment. Live coral branches frequently anastomose or fuse together, increasing the strength of the structure. Over thousands of years, large reefs may form with a live outer layer of coral over a core of dead coral and sediment. Lophelia petusa is arguably the most widespread and abundant of the reef-building species. It occurs most commonly in the North Atlantic, including the Mediterranean, Gulf of Mexico, and Caribbean, but also occurs in the South Atlantic, Pacific, and Indian Oceans. The shallowest record of Lophelia petusa was at 39 meters in the Trondheim Fjord, and the deepest was 3,383 meters on the New England seamounts. The largest known Lophelia reef is the Ross Reef off Norway, which is approximately 40 kilometers in length. This species is the most well-studied of all deep-water corals. Analopsamia profunda is limited to the western North Atlantic from Massachusetts on the east coast of North America to the Antilles in the Caribbean. It has a depth range of 403 to 1,748 meters and forms reefs sporadically along the Florida Hatteras Slope and Stetson banks. Many Analopsamia reefs are primarily composed of dead coral skeleton, particularly at deeper depths, but the reason for this is currently unknown. There are 2 deep-water Madrepora species. The one shown is Madrepora oculata and the other is Madrepora carolina. Both are often associated with deep coral reefs and contribute to structural complexity, but are not themselves primary reef-building species. Like Lophelia petusa, Madrepora oculata is a cosmopolitan species found in the North Atlantic from northern Norway to the Drake Passage in the subantarctic, whereas Madrepora carolina seems to be restricted to the western Atlantic. The shallowest record of Madrepora oculata is 55 meters off Brazil and the Norwegian fjords, and the deepest is off Iceland at 1,950 meters. Selanosimilia variabilis is generally cosmopolitan, but has not been found in the Antarctic or north and eastern Pacific. It is often found associated with other species such as Lophelia petusa, Analopsamia profunda, and Madrepora. Dense aggregations are found in the summits of Tasmanian seamounts in the Heesen fracture zone in the South Pacific. This species occurs at depths of 220 to 2165 meters, but is often found deeper than 1,000 meters. Goniocorella dumosa is most often found in the southern hemisphere near New Zealand, but also off Indonesia, Korea, and South Africa. It has a wide depth range, but is most common at 300 to 400 meters depth. Oculina varicosa is a rather peculiar species, as it most commonly occurs on nearshore hard substrate as relatively small zooxanthellae colonies, but the same species has formed large reefs along approximately 30 miles of the shelf edge at about 100 meters depth off the coast of Florida. These Oculina reefs are very similar in form and function to the deeper reefs, and they support very high invertebrate and fish diversity. Gold corals are members of the family Zoanthidae, which are usually soft-bodied, but members of the genus Gerardia form gold-colored proteinaceous skeletons, which are harvested for jewelry. The 3 species in this genus live exclusively in the deep sea, 2 in the North Atlantic and 1 in the Central Pacific. Gold coral colonies can reach up to 3 meters tall and are extremely long-lived. Black corals are so named for the dark protein and chitin skeletons, which, like the gold corals, are favored for jewelry and curios, especially off Hawaii, the Caribbean, Mediterranean, and Japan. The coral tissue is generally white, red, or orange in color. Black corals are distributed in deep waters throughout the world's oceans, from the Arctic Circle to Antarctica, in depths from 100 to over 8,000 meters. They can occur as single whip-like stems to large bushy colonies. Like the gold corals, some black corals may also be extremely long-lived, reaching hundreds to thousands of years. The Gorgonians are the largest group of deep-water corals, containing approximately 2,325 species that are globally distributed to depths over 6,000 meters. It's difficult to make generalizations regarding such a large complex taxa. However, there are several families that contain significant habitat-forming species. The family Paragorgidae contains 14 species of Paragorgia, commonly known as bubblegum corals. These can reach massive sizes, with colonies up to 10 meters reported off New Zealand. They have a cosmopolitan distribution and occur from 100 meters to over 4,000 meters. Unlike other Gorgonians, Paragorgia do not have solid skeletons, but a compact matrix of calcite spicules and organic material. Because these skeletons do not have the typical tree arrangement, determining growth rates is problematic. The family Corallidae contains the precious pink and red corals, which are commercially valuable, can reach up to 1 meter in height, and like the other precious corals, are slow-growing. The Primnoidae is a very speciose family with 7 genera containing potential structure-forming species, the most significant being Primnoa, which contains 5 species of large tree corals distributed throughout the Atlantic and Pacific. Finally, the Isididae, or bamboo corals, are unique amongst the octocorals for their skeletal structure of alternating Gorgonin nodes and calcium carbonate internodes, and these resemble the stems of bamboo plants, hence the name bamboo coral. Colonies of bamboo coral can be very large, up to about 3 meters in height. The stylasterids, or lace corals, range from Antarctica to the Arctic, and they are predominantly a deep-water taxa. They are generally distributed on the offshore slopes of atolls, islands, and seamounts, rather than on continental shelf habitats, possibly due to lower sedimentary regimes of features far from land masses. They generally have slow growth rates, long life, and brooded larvae, and may be outcompeted by more aggressive species in high-nutrient waters, finding refuge in low-nutrient or less competitive environments. Hydrocorals, like stony corals, have calcium carbonate skeletons, but are much more fragile than stony corals and do not form reef structures. They can, however, be very abundant and provide habitat for other fauna. The most notable area of hydrocoral abundance and diversity is on the slopes of the Aleutian Islands in Alaska. The soft corals, as their name implies, are soft-bodied corals with hydrostatic skeletons and small calcareous spicules. They are usually small and do not provide a great deal of structure, although they can be locally abundant and enhance habitat complexity. Sea pens and sea whips are octocorals, like the soft corals and gorgonians, but unlike most other corals which need hard substrates, the penatulids are found in soft sediment habitats. Some sea whips, such as the ones pictured here, form dense groves that create structure on otherwise featureless habitat and can provide shelter for other fauna. Sea pens and their relatives are very susceptible to bottom trawling, as they live in flat, soft substrate that is readily accessible to fishing gear. Sponges are a very important component of both shallow and deep sea systems. They are extremely abundant and diverse, but the total number of species is currently unknown. By far the most common type are the Dema sponges, which occur at all depth zones. The glass sponges are less common and are generally restricted to depths greater than 450 meters, although there are always exceptions. Like corals, sponges have complex structure that can provide habitat for other small animals. Amphipods live inside euplectile glass sponges, and cephalopods have been found inside tube and vase-shaped deep sponges, presumably for protection. In parts of the North Pacific, glass sponges form reef-like structures that serve similar functions to other complex reef habitats. Some fauna use defensive chemicals to protect themselves from predation, and this is particularly true of sponges. Many chemicals have chemicals in their tissues that are toxic or deterrents to potential predators. Some of these metabolically active chemicals have medical properties that have been used to develop human medicines, such as anti-inflammatory or anti-tumor drugs. In the early days of exploration, the ocean depths were mapped using weighted lines, which were laboriously deployed, measured, and recovered along a transect line. This was improved upon by the advent of acoustic mapping, where a single beam of sound was projected through the water and its reflectance time measured to provide a depth estimate. Today, a more sophisticated system of multiple beams allows a swath of seafloor to be mapped at once, greatly reducing the time required to cover a specific area and increasing the resolution of the data. These three-dimensional maps of the seafloor are a critical tool for exploring and conducting research on deep coral habitats, as they're used to target expensive underwater vehicles. Rocky complex habitats cannot be studied using conventional bottom sampling gear, such as dredges or trawls, as they're easily hung up and lost. Sophisticated vehicles such as submersibles or remotely operated vehicles are used for surveying these habitats, and such vehicles are not only costly but can only cover small areas of seafloor and can only be deployed in relatively calm seas. Despite these challenges, the use of underwater vehicles has greatly advanced our understanding of the distribution and ecology of deep corals over the past 2 decades. In addition to the underwater vehicles, other sampling gear is used to take supplemental information on the environmental conditions and from off-reef sites. These images show a plankton net in the top left, an otter trawl in the bottom left, a boxcore in the center, and a CTD Niskin array in the bottom right. These gears are used for collecting midwater plankton and nekton, collecting benthic fauna, taking sediment samples, and collecting data on the water column characteristics. Research cruises are of short duration, a month or so at most, and often much shorter. They are usually conducted during the calmer summer months to optimize data collection, and cruises therefore provide only a snapshot of information about these ecosystems. But understanding the environmental variability that occurs in these habitats is valuable in interpreting biological observations. To gain long-term data, moorings and benthic landers may be deployed. These are essentially frameworks on which a number of instruments, sensors, and experiments can be placed in order to learn more about the coral environment. Over the past 2 decades or so, considerable effort has been focused on the exploration and research of deep water coral reefs. While this has greatly expanded our understanding, there is still much to be learned about the basic biology and ecology of deep water corals and the communities they support. There are, however, some characteristics that seem to be common to most deep water coral taxa. Growth rates are generally slow, and this could be due to the low temperatures found in the deep sea, but many shallow water corals also have slow growth rates, so there may be some taxonomic constraints. Reef systems can be thousands to millions of years old, and some of the large tree corals exhibit extreme longevity. This trait provides a valuable archive of historical ocean conditions, as the coral skeletons reflect the ocean chemistry at the time of deposition. The vast majority of corals require hard substrate for successful recruitment and growth. There are a few exceptions, but even these require a small piece of rubble or shell for initial settlement. The requirement for current flow is common to all corals and is driven by their suspension feeding mechanism. Reproduction has been studied for a few species of deep corals, mostly the reef-building stony species, but also solitary stony corals and some black corals and some Gorgonians. All of the reef-building species have similar reproductive strategy, that is, they're all gonochoristic broadcast spawners that have external fertilization. Black corals are also all gonochoristic broadcast spawners, and hydrocorals are brooders. Other taxa have a wide range of reproductive strategies. Black coral skeletons are comprised of rings of a proteinaceous material that can be separated into individual bands to be counted and subsampled. The age of the skeleton can be estimated using isotopic signatures, and the growth rates estimated using a combined age, size, and number of growth bands. The skeleton can also be used as archives of temperature, mineral levels, nutrients, and pollutants. The oldest coral measured was a black coral from Hawaii, which was estimated at 4,270 years old, and provided an archive of ocean conditions from long before human records. How these corals grew under past conditions, especially in terms of temperature and carbonate chemistry, will provide insight into how they will cope with projected future changes. Other tree corals, such as the precious corals, are also long-lived. One gold coral specimen was aged at nearly 3,000 years old. The extreme longevity, slow growth, and unknown recruitment rates of these corals poses serious concerns over the sustainability of harvesting them. Coral reefs have been termed the rainforests of the sea because of the diversity of the coral reef communities. Deep coral ecosystems are similarly diverse, although unlike shallow reefs, which are comprised of many stony coral species, deep-sea reefs are constructed of one or two species of stony coral. Other deep coral ecosystems are dominated by Gorgonians or hydrocorals. The types of deep coral ecosystems can therefore vary greatly, but they all support an abundant and diverse associated invertebrate and fish fauna. Some of these associates are obligates and are not found outside the coral habitats. Many others are facultative, that is, they're part of the local deep-sea species pool and are found in other habitats. There are several measures of diversity. The simplest is simply the number of species present in the community. Others include measures of species abundance and changes in community composition over space, time, or environmental gradients. Either measure is challenging in highly complex deep-water systems as sampling capability is limited and rarefaction curves rarely reach their asymptotes. There have been many efforts to estimate diversity of deep coral ecosystems, but comparisons between these efforts have been confounded by differences in sampling methods, taxonomic emphasis, and level of resolution. Despite these limitations, there are a few general observations that can be made regarding deep reef biodiversity. Many new species and range extensions have been discovered as a result of focused research and intensive sampling using sophisticated underwater vehicles. New species have been discovered from almost every taxonomic group, especially among the invertebrates, and particularly those that are small or cryptic, or those that are very mobile, such as some crustaceans. As an example, a number of hydroids were collected from deep Lophelia reefs in the southeastern US. Of the 35 species identified, 2 were new species, 10 species in one family were new records for the region, 25 species were latitudinal or depth range extensions, and 11 species had not been reported since the early days of exploration. Crustaceans are the most diverse taxa associated with deep coral ecosystems in the western Atlantic and Gulf of Mexico, and probably elsewhere also. Common taxa include the galatheoid crabs or squat lobsters, brachyurine crabs, shrimp, and amphipods. This group is difficult to sample as they're highly mobile and either move up into the water column or into the coral matrix when pursued. For this reason, crustacean diversity associated with deep reefs is probably significantly underestimated, and some of the species associated with corals are of commercial importance, creating potential conflict with fishing gear. The galatheid fauna associated with deep water corals along the southeastern coast of the United States is quite diverse, with several undescribed species at the time of collection. Galatheids are often observed in association with various other animals, such as sponges, corals, and crinoids. However, associations seem to be facultative and not species-specific. The second most diverse taxa of invertebrates in the southeastern US were the echinoderms. There are several species of ophiuroids that seem to be specifically associated with particular coral species. The top right image shows the fleshy ophiuroid Asteroschema, which is frequently observed living in the branches of the Gorgonian Calagorgia americana delta in the deep Gulf of Mexico. Some asteroids are carnivorous on deep corals. The most commonly observed are members of the genera Hippasteria and Evoplasoma. Sponges are an extremely diverse group and are recognized as an important component of both shallow and deep reef ecosystems. A detailed study of sponges collected in box cores from Rockall Bank in the northeast Atlantic identified approximately 200 species. However, deep sponges are generally not well described. Improving the taxonomic resolution of both demosponges and hexactinellids will undoubtedly increase estimates of deep reef diversity. There are a host of other invertebrates and fish associated with these ecosystems, and few, if any, rarefaction curves are approaching the asymptotes for the invertebrates. Nearly all of the taxa studied have produced new species or range extensions, and the small and cryptic fauna are missing from nearly all of the studies. These are a few of the commercial and potentially commercial fish species associated with deep coral reefs in the western Atlantic. Some of these species are reef obligates, but many are also found in other habitats. The southeastern US and Gulf of Mexico deep reef fish are generally not targeted by fisheries. In the US mid-Atlantic region, species such as cusk and monkfish are frequently found associated with structure, but are also fished over soft-bottom habitats. Elsewhere, valuable fish stocks of fish species that are closely associated with deep reefs are targeted using heavy trawls that can severely damage benthic communities. As with shallow water corals, deep corals are threatened by a number of human activities. The greatest current physical threat to deep corals globally is bottom-tending fishing gear, particularly bottom trawling. Deep-sea fishing usually targets fish and invertebrates, but also includes targeted harvesting of precious corals for jewelry and ornaments. Deep-sea industries such as oil and gas extraction and laying of pipelines and cables may incidentally cause physical damage to corals, or release oil and other toxins into the water. Mining of valuable minerals is a developing threat in some locations, and the methods employed are extremely aggressive. Long-term effects of climate change are unknown, but will be more subtle and hard to define than the effects of fishing and industry. A bottom trawl is a net that drags along the seafloor. It is weighted with chain to keep it close to the bottom and is held open by two trawl doors. For large industrial trawlers, these doors may weigh several tons, and in rocky or coral habitats, rollers or rock hoppers weighing several hundred kilos are employed to protect the net from snagging. A single trawl pass can compromise a coral infrastructure, but many of these areas are fished repeatedly. Use of this type of gear over coral habitats has caused large-scale destruction in some regions. The panels show images of Lophelia habitat off Norway on the left and Oculina off the southeastern US on the right, before and after intense bottom trawling activity. The Oculina coral has not recovered despite closure to trawling and other activities since 1984. The precious corals include the red and pink corallium species, gold coral from Gerardia, and black coral from Antipotherians. These corals are slow-growing and long-lived, which makes them easily overfished with slow recovery rates. Precious coral fisheries use dredges, scuba, or even submersibles to collect specimens. Dredging is very destructive, and advances in technologies have removed previous refuges in deep rocky habitats. Precious coral fisheries are managed within some national EEZs, for example the US Hawaiian fishery, but harvesting on the high seas is uncontrolled and global demand is increasing. Efforts to obtain CITES protection for corallium species due to overharvesting failed, despite support from 62 countries. The fossil fuel industry has been operating in the deep sea for decades. Incidental and accidental oil release has caused severe acute and chronic impacts on both shallow and deep corals, either from direct toxic effects or reduction in oxygen content from bacterial metabolism of oil. The release of drilling muds and deployment of anchor chains have also caused some localized damage to benthic communities. Demand for modern technologies has created concerns over future supply deficits in some of the rare earth elements and precious metals used in their construction. The deep sea has reserves of some of these resources in deep-sea mud, polymetallic nodules, hydrothermal vents, and seamount crusts. There is global concern over how mining for these resources will impact marine communities. Mineral resources within national jurisdictions are managed by individual countries, and those on the high seas are managed by the International Seabed Authority. Millions of square miles of seafloor on the high seas are currently leased for exploration and extraction of minerals and rare earth elements. Those of particular concern for deep-sea corals are the cobalt-rich ferromanganese crusts that are found on the flanks and summits of seamounts, and which are also home to diverse deep coral communities. The map shows the known distributions of mineral resources, with the cobalt crusts indicated by red pentagons. Ocean temperatures have increased due to anthropogenic global warming, down to depths of 700 meters in some locations, although indicators of warming are complicated and vary greatly by location. Deep corals will have a species-specific tolerance to temperature increases, beyond which sublethal and eventually lethal effects will occur. These temperature limits are unknown for the vast majority of species. It has been estimated that the oceans have absorbed approximately one-third of anthropogenic emissions, which amounts to about 525 billion tons of carbon dioxide. When carbon dioxide dissolves in seawater, it reduces the pH, creating acidified conditions. Reduction in pH changes the ocean chemistry so that carbonate ions become less available for deposition of skeletal material. Models have indicated that continued business-as-usual emissions scenarios could cause reductions of about 0.7 units by 2100. The effects of acidified conditions on calcified organisms are not well understood, and limited data from Lophelia producer experiments have indicated some level of resilience to reduce pH, although there was probably an energetic cost and certainly a limit to the coral's ability to compensate for reduced pH. Unlike physical damage, the effects of climate change may permanently undermine potential recovery because new suboptimal conditions prevent successful recolonization. There is some experimental evidence that some species can physiologically accommodate some fluctuations in temperature and reductions in pH. However, as with all physiological compensation, this tolerance has limits, which once exceeded will ultimately result in mortality. These are some examples of how different countries have enacted measures to protect sensitive seafloor areas, including deep-water corals. These protected areas have a variety of different regulations, ranging from simple fisheries closures to more restrictive measures that control a range of activities. Place-based measures only prevent physical damage. They do not protect against oil spills or the effects of climate change, for example. But an intact and healthy ecosystem tends to be more tolerant of negative impacts than one that is chronically stressed from repeated damage. Protected areas may therefore confer some level of resilience to environmental changes and pollutants. The high seas, or areas beyond national jurisdiction, pose an even greater management challenge than areas within national EEZs. Activities on the high seas are overseen by the United Nations, which implemented Resolution 61105 in 2006 in response to a call for a moratorium on deep-sea bottom trawling. This resolution committed those nations engaged in high seas bottom trawling to take actions to protect vulnerable marine ecosystems, or VMEs. In 2009, due to lack of progress, the UN implemented Resolution 6472 that reaffirmed the previous resolution with additional guidelines. Some progress has been made, but the problem of coral habitat destruction has by no means been resolved. Regional fisheries management organizations are responsible for fisheries management on the high seas within the different regions, but not all areas or stocks are covered by these entities. The OSPAR Commission, which comprises representatives of 15 countries, cooperate to protect the marine environments of the northeastern Atlantic, originally from dumping of hazardous waste, but now the convention includes other activities such as fishing. CAMALA is the Commission for the Conservation of Antarctic Marine Living Resources, which has prohibited bottom trawling and has implemented a move-on rule, whereby any vessel encountering vulnerable marine ecosystems must move away from the area and report the encounter so conservation measures can be adopted. All of the above regulations apply primarily to fishing. The International Seabed Authority is responsible for management of high seas mineral resources and is currently under pressure to develop areas that are closed to mineral extraction to protect deep-sea ecosystems. High seas governance is very complicated and fraught with problems, particularly from illegal, unreported, and unregulated fishing and the use of flags of convenience. But to end on a positive note, public awareness has increased greatly over the past 2 decades, which has applied pressure to management entities to enact conservation measures. Several nations have established protected areas and fisheries closures to protect deep corals, and there are some regional and global efforts to protect sensitive deep-sea ecosystems on the high seas. This presentation was a very superficial overview of the current state of knowledge of deep-water coral ecosystems, but I hope served as a useful introduction to these remarkable, valuable, and fragile resources.